We've seen a first basic model for the spread of an epidemic disease, the branching process model. And what was nice about it is that it had such a clean, simple structure that we could actually analyze completely what would happen to the epidemic in that setting. But on the other hand, the very simple structure means it's sort of hard to incorporate features that we know are true about social networks, right? And in particular, this idea that each person goes out and meets K completely new people and has a chance of infecting them ignores the fact that, of course, real social networks close back in on themselves, right? So your K friends that you're in contact with, of course, they also go and then meet each other, right? And that's what forms triangles, you and two of your friends who know each other. And the contact network for our branching process had no triangles whatsoever. In that sense, maybe it made sense for people just going out into a big crowded city, though even there it's questionable. But certainly it makes less sense for a disease that's spreading on a social network that has all the rich properties that we know those networks do. So what would be a reasonable model for epidemics on networks in general? And what we can do is sort of take the ideas that were going on in the branching process model and simply try to adapt them to the network setting. And maybe the simplest way to do that is through this model called the SIR model. And SIR stands for susceptible, infectious, and removed. And let me explain why it's called that. So in this model, what we're doing is we're taking a social network or a contact network among people where each node represents a person. And let's say there's a directed edge from one person to another if the first one is going to come in contact with the other one and potentially infect them. Okay. Now, we're going to try to track the changing states that these nodes go through as the epidemic proceeds. And, say during flu season, you could think of it as, you're going to be in one of three states during flu season. You could either be, at the start of flu season, you're susceptible to the flu. You haven't caught it yet, but you might. If you then catch the flu, right, you have all the symptoms and you're contagious, then you're in the infectious state, right? So in a sense, you are a danger to other people you bump into because you could make them sick. Right? So now you're in the infectious state, right? You've gone from susceptible to infectious. And finally, you recover. And now once you recover, your body is filled with sort of, antibodies, natural defenses, and so forth. And so you're unlikely to catch it again, right? So not only are you no longer contagious, you're also no longer really likely to be someone who can carry the flu and transmit it onward, right? That's not a perfect picture, but other diseases really do much more reliably confer even lifetime immunity. And so at that point, we'll say you're removed from the system. Right? You're removed because you are no longer part of the network on which the epidemic can operate. You're sort of like a blocker for it. Okay. And over the course of this whole epidemic, nodes can pass through that sequence of phases. They start susceptible, they can become infectious if they catch the disease, and when they recover, they're then removed, right? Because in this model, you're not going to catch it again. Okay. There are, of course, other diseases that fit less well in this model, right? Maybe after you're infectious, you are temporarily safe, but then you go back to being susceptible. So we could dress up this model and make it more complicated. But this is maybe the simplest way to look at it. Okay. We're also going to bring back in this probability of P, right? We're going to model contagion as random. So we're going to say, here's what happens from one node's experience, right? So you start out susceptible. If you catch the disease, you are now infectious. And now for one time period, while you're infectious, you have a probability P of infecting each of your susceptible neighbors. Right? So with each of your neighbors for that one time period when you're sick, a coin gets flipped with probability P on heads. If it comes up heads, now they're sick also. Okay? And the disease goes on this way. After that one time period, you switch from state, the infectious state, to the removed state, to state R. So we could think about this in a simple example, right? So in this simple 6-node graph, there are 5 susceptible people, and there's patient 0, right? Patient 0 is infectious. We're not sure where they got the disease, but they showed up and they have it. Okay, and now for that one time period, they have a probability P of infecting each of their 3 neighbors, right? And maybe we run time forward, and they actually infect 2 of them. So at the end of that time period, we now have 2 infectious people, the 2 friends who caught it. And meanwhile, patient 0 is now removed from the system. They're no longer infectious. Okay. Now, these 2 infectious people have a chance of infecting each of the 3 susceptible people. One of them actually has a double chance, right? So on each of those links, there's a probability P that they might actually catch this thing. And so we flip those coins, and maybe what happens is only the top node actually catches it. The other 2 don't, right? The lower susceptible person actually survived both attempts to infect them. And now those 2 people, sick people, are removed. right? And there's one last infectious person in the network, but that one last infectious person is sort of blocked off from the rest of the graph because their only neighbor is removed. And so we know that at the end of this time step, they too will be removed. And now the epidemic has run its course. 4 people got sick. 4 people are now removed from the system. They got over the disease, they recovered. And there were these 2 people who never got sick at all and aren't going to get sick because there's no more infectious nodes in the entire system. Okay? And that's a sample run of the SIR model, right? It tracked the changing states of nodes during the course of an epidemic from susceptible to briefly infectious while they have disease and are contagious to removed, where they can no longer either catch it or transmit it. Okay, if we think about it, actually, this model is not just sort of richer than the branching process model, it actually contains the branching process model inside it as a special case. Because, in fact, the branching process model is simply an instance of the SIR model running on a particular contact network, right? What is that contact network? It's this infinite branching tree, right, that starts at patient 0, and each node in this contact network has k nodes directly below them, and those k nodes, each of them has k nodes directly below them, and it continues on forever, right? So the network never has no cycles, it doesn't loop back on itself, it just goes on forever all the way down. Okay, that's the contact network. And what we had described as the branching process model really is just a run of an SIR epidemic on this infinite tree. Start with patient 0 in the infectious state, start with everybody else in the susceptible state. And now patient 0 has a chance to infect each of these k people. And when that happens, patient 0 is now removed, some new people are infectious in the first wave, and they now have a chance to infect people in the second wave. And the disease runs on, and it either ends with this finite clump of removed nodes, and everyone else is susceptible but safe because there's no more infectious nodes. Or it can keep going, keep running forever, generating deeper and deeper infectious nodes down the tree as it continues on its way. And so that dichotomy in how branching processes behave was really simply a dichotomy about how SIR epidemics behave on this particular kind of contact network. And the point was that this particular kind of contact network was simple enough that we could actually analyze it completely. But that actually changes when we start looking at just general networks that characterize arbitrary social networks. And in fact, it's very, very complicated to figure out the likely course of an SIR epidemic on an arbitrary graph, arbitrary social network. That turns out to be sort of an active area of research. It's a mathematically very challenging question. It's something where one often resorts to computer simulations, for example, rather than being able to do some kind of closed form analysis of it. And in particular, there isn't really a good analog of the basic reproductive number, right? You could still say in an arbitrary graph, for each case of the disease right now, what's the expected number of new cases it creates? But somehow that number on its own doesn't actually capture everything that's happening when you have a rich, complicated graph. So this now takes us to a first model that lets us talk about arbitrary network structures and an epidemic that operates on it. Of course, the theory of epidemics and the practice of analyzing epidemics goes much, much deeper than what we've been able to talk about here. And it's really a topic that has both a number of elegant models and lots of data that people can study from actual disease outbreaks. And there are many issues that people study here, right? Including the fact that, of course, susceptible, infectious, removed is a very simple kind of cycle for a disease. But you could, for example, have diseases that you're susceptible, you're sick and contagious for a while, you have temporary immunity, you go back to being susceptible. New strains of the disease can come in, right? Slight mutants of the old one that have different contagion properties. And of course, contact networks can change over time, right? You can sort of be in contact with people for a while, then you're not. And of course, even as the disease is running, in reaction to public health measures, people might sort of stop gathering in big public places, the network will change. All of these are factors that come into the building of models for epidemics, and collectively it becomes a rich area where networks can inform public policy, in this case public health policy, about a very important and often consequential issue.